Let's take a look at example 3 of chapter 14.6. We want to evaluate the triple integral from 0 to radical pi over 2, from x to radical pi over 2, from 1 to 3, of sine y squared dz dy dx. This is an example where we actually want to do a change in the order of our integration as it pertains to the region. What would happen if we were to try and go through and do the first integrating this thing with respect to dz? Upon doing that integration by doing z first and then trying to do y next, would produce the integral 2 times the integral of sine y squared dy, which is not going to be an elementary function. So what we're going to want to do is change the order of integration so that we actually get a second step that will be integrable, and so that we can actually calculate this thing. Okay. Let's kind of investigate the region that we're looking at here. If we look at the bounds for z, we see that z, which is the innermost integral variable of integration, is going to range from 1 to 3. So z ranges from 1 to 3. We see that y is going to range from x to radical pi over 2, and that dx is going to range from 0 to the square root of pi over 2. If we want to, we can kind of take a look at this region. So here, looking on the vertical scale, this is our z values. They range from 1 to 3. We see that in the xy plane, if we look at the projection of this region, x ranges from 0 to the square root of pi over 2, and y itself also ranges from 0 to the square root of pi over 2. Let's change the order of integration so that we can actually integrate this thing. One of the orders of integration that would work for us is if we can change this to an integral, a triple integral, and let's use the following order. Let's do the integral dz dx. This originally should have been dx, and then dy. In other words, we'll save the integration with respect to the y variable for the very end. We still need to find our bound. So the bound for integrating with respect to dz, this is still going to go from 1 to 3. And originally we had this. We know that 0 was less than or equal to y, which is less than or equal to the square root of pi over 2. And x was such that it was greater than or equal to 0 and less than or equal to the square root of pi over 2. Well, this also tells us, because of this, we see that in terms of the bounds for the variable x will be between 0 and the y value. So that's our bounds for x, and y will still range from 0 to the square root of pi over 2. So we can change the order of integration, and let's see how this impacts our ability to actually find this antiderivative. This will be the integral from 0 square root of pi over 2, the integral from 0 to y. With respect to z, sine y squared is a constant, so that antiderivative is z times the sine of y squared, which we'll evaluate from 1 to 3. And then we're going to do dx dy. We plug 3 in for z, subtract what we get when we plug 1 in for z. We get 3 sine y squared minus 1y squared. Let me write that out. dx dy. Before we do our next integration, let's combine those like terms. This is equal to the integral from 0 to the square root of pi over 2, the integral from 0 to y of 2 sine of y squared dx dy. The nice thing is that with respect to x, 2 sine y squared is constant, so we get the integral from 0 to radical pi over 2. This is going to be 2 sine y squared times x, evaluated from 0 to y, dy. Oops, let's undo that. When we substitute in y for x, it will produce the following. We're going to have the integral from 0 to the square root of pi over 2. This will give us a 2 sine y squared times y minus 2 sine y squared times, when we plug in the lower limit of integration, this is 0 dy. So it boils down to doing 2 times the integral from 0 to the square root of pi over 2. I could have left that 2 on the inside, doesn't really matter. We have y. Actually, let me bring it back in. We have 2y, and then we have the sine of y squared dy. And what's nice now is the fact that we switched the order of integration, and we're now saving the integration with respect to y last. As a result of our previous evaluations, we now have this extra y term out in front of the sine squared, which will allow us to actually do the integration. This is a simple u substitution. Let u be the y squared, the part that's on the inside of the sine. Our du would be equal to 2y dy. So this is going to end up being equal to the integral. 2y dy is going to be my du. This is going to be the sine of u. And then we should also change our bounds as well. When y was equal to the upper bound of radical pi over 2, u will be the square root of pi over 2 squared, which is pi over 2. And when y was equal to the lower bound of 0, u, which is equal to y squared, will be 0 squared, which is 0. So this now goes from 0 to pi over 2. The antiderivative of the sine is the negative cosine of u, evaluated from 0 to pi over 2, which is the negative cosine of pi over 2 minus the negative cosine of 0, which is going to be 0 plus 1, which is 1.